Today's lesson is about Ftir, which stands for Fourier Transform Infrared Spectrometry. So IR is a type of absorbance spectroscopy. And in this case, it's not nearly as high an energy level as UV vis. So if we wanted to draw a energy kind of level diagram, if these were our excited energy states, and this was my ground state, right? If I were to go all the way up here, right, that would be what I would see in UV vis. I get up to an excited singlet state. But in here, IR, we don't have that much energy. The energy of the radiation is much lower. Instead, it goes to smaller levels that are down here. So our absorbance that we get are down here. And what are these levels? They're primarily due to different vibrations of the molecule. So these are our vibrational energy levels. And so as the molecule vibrates and or rotates, they're sometimes called rotational levels as well, it can absorb energy basically as its bonds undergo vibrations. And so the main rule for IR, whether something is going to have the bond is going to have a vibration in the IR, is that you need to get a change in the dipole moment. And so things that don't have a dipole, so things that are symmetrical like N2, O2, etc., have no IR because you can't get this change in the dipole. That doesn't happen. But most of the molecules, right, have some sort of bond that has some sort of dipole to it. The electrons are not shared evenly, and so that we can get things into vibrational states. And so most things are IR active. We're going to be doing a special type of IR. Almost all of the instruments now are FTIR, where again FT stands for Fourier Transform. And this is just a fancy mathematical concept that allows you to go back and forth between the frequency domain and the time domain. And so instruments that have Fourier transforms in them tend to be fairly precise because it's easy to measure things specifically in the time domain and then go back and forth to the frequency domain. We're not going to spend a lot of time on the FT part today. So let's look under the hood of an FTIR for a minute and discuss what's in the instrument. Okay, so if you were to go to a standard textbook, it would probably draw you an FTIR that looks something like this. So we have to have some sort of light source, and you probably would put it through some sort of collimator, something that's going to line up the light. Once it does that, it's going to go through to something that's called a beam splitter. And so this beam splitter, what happens is that half of the light gets reflected up and half of the light goes through that direction. And both of those lights hit a mirror. This light up here hits a stationary mirror. So that mirror is always fixed, and once it hits that, it goes back down through this way. This light over here hits a movable mirror. So that mirror can be in different spots. And once it goes there, it goes back down and goes down this way. And so these two things of light will recombine. And then I didn't draw my sample in here, but we're going to have some sort of sample, right? So I have the two parts of light that are going to go through, and then afterwards some sort of detector. Okay, so we're going to look at absorbance measurements here. And so what happens is that this mirror moves And in light, there's something called constructive and destructive interference. And so you get out a signal that kind of looks like this, where the axes on this would be the movable mirror, like kind of distance. So where is it? And so what you do is you move this mirror in time. So there's also an element of time to this. The movable mirror, and then, you know, some sort of absorbance kind of signal. So when these two are exactly aligned up, they will come through the sample. There will be more radiation, and then the sample will be able to absorb it better. And so from this, then, this is in the time domain, they Fourier transform it, and they get some sort of UV vis, sorry, not UV vis, FTIR spectrum. Now, it depends on how they draw it. In organic class, you might have seen them draw a spectra like this. If you're drawing it like that, that means that the y-axis is transmittance, because this would be 100%, right? And so as it absorbs, peaks that absorb go down. This is almost always wave number down here in inverse centimeters. That's where IR is done. Sometimes now you'll see a spectra instead that shows you absorbance. No biggie, right? Absorbance is just 1/T, so that you can see that. Oops, I drew that a little bit off the board. I'll draw it up here. So you can see the absorbance spectrum there. Okay, so it can look either way. Okay, so that's a general FTIR. We have one more feature on our FTIR that's even better. So we're going to hone in on this sample part for a minute and learn about the special feature of our FTIR. So our FTIR has something that's called ATR. Everything is an acronym in analytical chemistry, and that stands for attenuated total reflectance. So normally for a sample, right, for any type of absorbance, FTI or UV vis, right, you shine your light through, you see how much is absorbed. And as we all know for Beer's law, absorbance is proportional to the path length. Well, in attenuated total fluorescence, what they have is some sort of ATR cell is what they usually call it. And then you could go ahead and you put your sample, let's put our sample in red. We'll put our sample on top of it. And now what they do for this ATR is that they shine the light in. The light's going to come in at some sort of angle such that it's going to bounce and be reflected. So that's the total reflectance kind of thing. And go up and interact with the sample. Now every time it comes up in here, you'll see that it actually penetrates the sample a little bit. So some of the light can be absorbed, right? It interacts with the sample. There's whole bunches of equations that'll tell you about this. But basically, the path length, what I want you to get out of this is that the path length ends up being a lot longer. And it's longer due to basically the things that it matters are the penetration depth, so how deep it goes every time, and then the number of reflectances. And so we end up getting much higher absorbance because we end up having a much larger path length. So this is a really sensitive instrument. So if you were to make something that would reflect like this, what would you make it out of? It turns out that ours are made out of diamond. So you think, oh yeah, diamond, pretty clear, reflect light, that sounds all good. So ours are made out of diamond, and that makes them, number one, very fragile, and expensive. So the thing that we put our sample on, the ATR cell, is like $10,000 in the lab. and it's very easy to break. So please, you have to treat it with utmost care, not to scratch it, not to break it, not to do anything that's going to kind of mess with the surface. But this makes it a super, with the ATR, it makes it a super high sensitivity instrument. Okay, so that's what we're going to be looking for. So for IR, we typically then just match spectra and look for different features in the spectra in the different regions. We can use it quantitatively if we want to look at how different peaks go, but most of the time we're just going to be looking qualitatively, matching up peaks, right? And so it's the number one thing, right, that FTIR is really known for, right, FTIR is really known for, right, is going to be able to identify functional groups, like different functional groups have absorbances at different wavelengths or wave numbers, and we're going to be able to do that. And again, if we match the spectra, we should be able then to identify unknowns. And we have started to make our own library with our FTIR in the lab of different compounds that we can try and match spectra, and those libraries you can buy as well. Okay, so that's the basic overview of FTIR spectroscopy.